All right, let's take a look at some of the habits of mind that deal with lab exercises. We'll begin by looking at some data that was obtained from a basketball drop. In this experiment, a basketball was held beneath a sonic ranger or the CBL, and this motion detector device was able to plot the position versus time for our particular basketball as it fell to the ground. We're only interested in the motion of the basketball until it reaches the ground. So we're going to end up taking that data and cutting out the data that we don't want and just holding on to the data that we do want. We're going to call that process culling, Culling, or cutting out certain parts that we don't want. Let's just take a look at the raw data that was brought in from the Logger Pro software. Now, in this particular data set, we actually have time, position, velocity, and acceleration. We're just going to take a look here at the time and position. That's what we'll be working with. You can see that the position is fairly constant up until a certain point, and then it starts to get larger. And that would be, where we begin to accelerate or let go of the basketball. You can see there is some variation even before the basketball really starts to take off in speed, and that's just due to the hand moving a little bit prior to the release of the basketball. To make this easier to cull, we're going to move it from this plain CSV file into a spreadsheet, a Google spreadsheet, and go ahead and cut out the data. So let's go into a Google spreadsheet. I actually created one over here where I've isolated the necessary data. I initially was creating a chart of the scatter plot of the data so I could take a look at where I needed to cut out, where it started to accelerate, where it hit the ground. So that's the process you need to go through when you are prepared to start cutting things out or culling. Down here below, you can see my resulting data, and it's very nicely presented. I am starting over here with an initial position of 0.235 centimeters. I'm sorry, 0.235 meters, or 23.5 centimeters away from the motion detector when it was released. And then we have the acceleration here over time. And this is about where it hit the ground. If you looked at the initial data, you would have seen that it would have kind of went through a bouncing pattern at that point. Okay, so once you have culled the data, you need to do what I've done to obtain this. You have to move back the time from when the release happened. So if the release was at 0.8 seconds, like this was, my release was at about at 0.8 seconds. I made a new column over here, and I called it adjusted time. And if you look at what went in this cell, it's just the time that was in the original time. And that's up here, minus 0.8, because that's the time that the release happened. That's when I let go of the basketball, basically. So by doing that, then I translate horizontally the graph to the left, and then essentially I'm able to have a better comparison to the model that we're going to use. Okay, so here's the data down here in this region, starting at cell B17 basically up to cell C26. That data, I just copied that data and I put it into zunzun.com. If you look over here, here's that data in zunzun.com. Notice the initial position is 0.235 meters. Okay, and that's important. That's I know what that position is, so I can force my when I'm doing my modeling, I can force my coefficient, my position, initial position coefficient to 0.235. We also know that I was holding it still at the very beginning before I dropped it, so we can also force our velocity coefficient to 0. So let's go look down here under holding coefficients constant, and you can see I did just that. Over here is my initial position coefficient. my A, that's 0.235, so that's the initial position. And notice that I'm holding the linear coefficient to 0, holding it constant at 0 because that was my initial velocity. And then I've also done one more thing under the enter coefficient bounds. My acceleration, since my motion detector is pointed down, down becomes the positive direction, and I'm going to obtain a positive acceleration. So that means I can put a lower bound on the acceleration of 0. So that would be another constraint that we add before we actually run the regression. Other than that, what else did I do? I put data labels over here for the X data is going to be time, the Y data is going to be the position in meters, time in seconds, position in meters. And we can expect then to get a result. If we look down here for the coefficients, we can expect our C, which is allowed to float, our C to give us our value for 1/2 the acceleration based on our physics model. So let's go ahead and see. I think I have everything else set up. So we can submit this. And it's given me some information about the server and how much it's doing in terms of work for other people. Okay, here we go. So I'm going to select over here coefficient and fit statistics, and they appear right down here. Let's take a look at them. Notice we had fixed A, so this really doesn't mean much. We fixed B. Well, it does mean something. I'm sorry. This does mean that we started, 23.5 centimeters away from the sensor, from the motion detector, and this means that we had an initial velocity of 0. Down here, this is the interesting part. This is what is relating to 1/2 of our acceleration value. We would expect 4.905 to be so 4.905 is what we would expect to be a perfect match with the theory. We're coming in a little bit high, which could just mean that I called it a little bit off when I was culling the data. There could have also been a slight bit of downward motion. My hand might have been moving a little bit down as I released it. So there's a couple of things that could have factored into that being off there. But if you look at it, let's take a look at the 95% confidence interval. And it takes us from 4.7 to up to 5.6. So, we're comfortably, the value that we want, our expected value is 4.905 is right in that confidence interval. So that's a good thing right there. We'll tell more about this when we run the, percentage difference, and we'll do that in class. And I'll do this as an example, and I'll run the percentage difference on it. But what I would do with this data is I would just paste this directly into a page in the in my website. So in your website, I'd expect you to just go ahead and just dump this into your page, and it will be then we'll be able to use it and write up an analysis based on this as well as a graph. So let's generate a graph next. Let's go over here and so maybe I'll just submit it again so I can keep that other tab open. And then what we'll do is we'll generate a graph, and we'll put some things on the graph. So over here, we can, if I pull it over onto the screen so we can see it better, we will generate a position versus time graph. And we're going to have the 95% confidence intervals on it. So let's take a look at that. Whoa, that's looking pretty good. In terms of the confidence intervals, we're seeing a number of our points are right within the dash line. We have some points that are right in the dash line, some that are kind of like right on the dash line. So we're pretty close with a lot of these. It's a fairly good fit. We would like as much of these original data points in green to appear within the 95% confidence interval, which would mean between the two dashed lines that are drawn about the model line. So the model line, which is the line of best fit, is the solid black line that you see curving up and to the right. The original data are the green points, 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10, I think. Yeah. And we have several, several, at least two right here, three, I would say three that are, clearly out, three that are clearly outside of the 95% confidence interval, but the rest of them seem to be either in or very close to in the 95% confidence interval, and that's per data point. Okay, so that's fairly accurate in terms of matching of the raw data, the data from the experiment. I shouldn't say the raw data, but our data after we adjusted it. Our data is a fairly good match with our theory. Okay, I would then take this particular graph as well, and I would save it as a picture. I just right-click and save it as an image, and I would save that, and I would also put that into my website and use that in my write-up. So in my write-up for this lab, I'll need or you'll need to have the same type of information. You'll need to have this particular type of information here, which includes the actual coefficients. And the statistics. I'll talk to you more about these statistics that are in here. I would just take this entire page. One thing that I want to point out right here that we will talk about a lot is the R squared value. Okay, the Pearson's coefficient of determination. And notice it's 99.9. And that is a very good fit. That's a very good indicator. When we do our percentage difference, you'll see that it'll also be up there as well. Actually, our percentage difference is going to be small. Our R squared value, or our Pearson's coefficient of determination, which we'll talk to you more about later, is looking good, because the closer to 1 that this is, the better it is. All right, so this should all go into the website, and the graph make sure you include the 95% confidence intervals so you can discuss them, and how our data points, at least a majority of our data points, are either close to or clearly within the 95% confidence interval lines, and just a few of them are outside or on the or nearly on the confidence interval lines. So that's what I want you to be able to get into your site, and then I'll go more into the expectation of how to discuss it, how to create the actual write-up in terms of the wording that you should use and so forth. But that's kind of like the mechanics of the stuff you need to get in there. All right? So I hope that helps you, and I'll see you soon.